Good morning. In the previous lectures we covered the continuous distributions, the uniform and the normal distribution. Today's lecture will cover a new topic. Today we will talk about the sampling distributions. From the name of the topic, sampling distribution, it's clear that we will talk about something related to sampling. So it's good to start with the possible reasons for sampling. Why do we need to take a sample in many practical situations? First of all, sampling, of course, will save money, will save time. In addition, in many situations, the research process itself is destructive. For example, if I'm trying to test the quality of my production, and suppose that the testing procedure itself is destructive or can cause a damage to the product units. In this case, if I apply the testing procedure to all the units of my production, if I apply the procedure to all the members of the population, then in this case I will end up with a totally damaged production or a totally damaged population. So in this case, the reasonable solution will be to take a sample of your production and then apply the testing procedure to this sample, and in this case you can save your product. Okay, the last reason or the last possible reason for sampling is that in many cases accessing all the members of the population is impossible. So in this case the sampling is the only option I can make. Now recall that the main target of this course is related to the process of inferential statistics. And in inferential statistics, my main target is the population parameter. The population parameter, as we studied before, is some measure computed from the whole population. So, if my population is all the workers living in Egypt, and if the measure I'm interested in measuring is the average wage of all the workers living in Egypt, and if accessing the members of the population is impossible for any reason, then the reasonable solution is to take a sample from this population. For example, to collect data from a small portion of the workers. Okay, in this case, I can compute the average wage based on the sample data. And using certain statistical tools, the tools we will call the inferential statistical tools, I can reach a conclusion about the population parameter. I can reach a conclusion about the wage, the average wage of all the workers living in Egypt. So this is the process of statistical inference. You need to know something about the population. You need to know some measure about the whole population, about all the workers living in Egypt in our example. You don't have access to this population, so what will you do? You will go and take a sample. From this sample you will compute the same measure. If I need to measure the average wage from the population, I will go and compute this measure but based on the sample. Okay, and using certain inferential statistical tools, I can make some kind of inference about the population parameter, about the population wage of all the workers living in Egypt. So this is the process of statistical inference. Now let's move to the definition of sampling distribution. What kind of distribution are we talking about when we mention the word sampling distribution? From its name, it's clear that the sampling distribution is the distribution of something computed from the sample. The sampling distribution is the probability distribution of a sample statistic. Now let's return back to our example. If we are interested in measuring the average wage of a worker living in Egypt, so the population of interest is all the workers living in Egypt. From this single population, I can select different samples of workers. For each of these samples, we can get a different value for the sample mean wage. So the sample mean wage is not constant. It's changing from one sample to the other. So if we imagine that we are listing all the possible values for the sample mean and their corresponding probabilities, then this kind of listing will represent a probability distribution. But keep in mind, in this case, the probability distribution is a probability distribution of the sample statistic. In this semester, we will always assume that we are either sampling from an infinite population or that sampling is done with replacement. By with replacement, we mean once we select a unit from the population, we should replace it back. The displayed figure will elaborate the idea of the sampling distribution. The sampling distribution of the sample mean. We have one population and we can select different samples from the same population, and hence we will expect to have different values for the sample mean, making this sample mean a random variable with a certain probability distribution. In this semester, we will study the sampling distribution of the sample mean x bar. The sample mean x bar is used to estimate the population mean mu. It's important to point out that we can also study the sampling distribution of other sample statistics, like the sample proportion or the sample variance, for example, but this will not be covered during this course. Okay, so let's now move to the sampling distribution of the sample mean x bar. The sample mean is one of the most common statistics that we will use in statistical inference. If I need to find the probability distribution of the sample mean or the sampling distribution of x bar, then I can try to list the possible values for the sample mean and their corresponding probabilities. Okay, so let's clarify this more in the next slide. Okay, so let's take an example on the sampling distribution of x bar. Now a fair die is rolled once and we are interested in the number of spots that I will get. We know that when we roll a die we can get a 1, 2, 3, 4, 5 or 6, and we know that the probability of any outcome of the 6 outcomes is 1 over 6, as we can see in this probability distribution table. We also know that to compute the mean of any discrete distribution, I can use this rule, summation x times px. So to find the mean of the number of spots, I will multiply 1 times 1 over 6 plus 2 times 1 over 6 plus 3 times 1 over 6 plus 4 times 1 over 6 plus 5 times 1 over 6 and finally plus 6 times 1 over 6. This will give me 3.5. So the expected value of the number of spots that I will get when I roll a die once is 3.5. As for the variance of the number of spots, we will use this rule, the rule of the variance of any discrete distribution. This is summation x minus mu all squared times px. So let's apply this on the previous table. So I will use 1 minus mu 3.5 all square times the corresponding probability 1 over 6 plus 2 minus 3.5 all square times 1 over 6 the corresponding probability, and we will follow the same procedure on all the numbers until the last value, which is 6 minus 3.5 all square times 1 over 6 the corresponding probability. This will give me 2.92. so this is the variance of the number of spots. Of course, to find the standard deviation of the number of spots, I will just take the square root of the variance, so the standard deviation for the number of spots is 1.71. So let's now imagine the sampling distribution of the sample mean through this example. Okay, in the previous example we studied the distribution of the number of spots that I will get when I roll a die. Now let's imagine the experiment when a die is rolled twice. Okay, we will have 36 possible samples, as we see. 1 on the first roll, 1 on the second roll, 1 on the first roll, 2 on the second roll, 1 on the first roll, 3 on the second roll, and finally 6 on the first roll and 6 on the second roll. We have 36 possible outcomes. Why do we call them 36 possible samples? Because we can imagine this experiment as the experiment of having a population of 6 numbers. The six numbers that I can get when I roll a die, 1, 2, 3, 4, 5 and 6, and we can imagine that as if we are sampling 2 dice rolls from the 6 numbers, okay, because we are rolling the die twice. So the 2 dice rolls, as we see from the 36 samples, can be 1 and 1, 1 and 2, 1 and 3, up to the last possible sample, 6 and 6. So at the end we have 36 possible samples when I roll a die twice. Okay, so how many values do I have for the sample means? Okay, here we have 1 and 1, the corresponding sample mean for this sample. Okay, so we have 36 different samples. We are trying to find the corresponding values of x bars. For the first sample I have 1 and 1. The sample mean is 1 plus 1 over 2. This is 1. The sample mean, the second sample mean is 1 plus 2 over 2. 3 over 2 is 1.5. The third sample mean is 1 plus 3 over 2. This is 4 over 2 or 2. For the last sample, 6 and 6, the mean is 6 plus 6, 12 over 2. This will give me the 6. So at the end, I have 36 possible samples and 11 different values for x bar. So let's see. The different values for x bar are 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5, 5.5 and 6. So we have 11 different values for x bar. Some of these x bars are more frequent than the other values. Yani, for example, if you notice the values of x bars in the display table, you can notice that the value of x bar 3.5 occurs more frequently than the value of 1, for example. So some values are more frequent than the other ones. Now we will try to construct the sampling distribution of the sample mean. By the sampling distribution, as we said before, we will try to list the different values of x bars, the different values for the sample mean, and their corresponding probabilities. Now let's try to construct the sampling distribution table of x bar, or the probability distribution table of x bar. This is the table we constructed before. We have the 36 possible samples in our example and the corresponding values for the sample mean. We can construct this table by listing the possible values for x bar. So to start constructing the probability distribution table of x bar, I will list the possible values for x bar. The possible values are 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5, 5.5 and 6. So we have 11 different values for the sample mean. Okay, we can compute the probability of each of these values. How can I compute the probability that x bar will take a value equal to 1? I will return back to this table, search for the value of 1. I will find that 1 occurred only once in the values of x bar. So its probability is 1 over 36 because I have 36 possible outcomes. What about the probability of the value of 1.5? I will return back to this table. This is 1.5 and I will find another one. So 1.5 occurred twice, so its probability is 2 over 36 because I have 36 possible outcomes regarding the value 2. So let's return back to this table. This is the value 2 and 2 is repeated here. We have a third one there, so we have a probability equal to 3 over 36, okay, because the number 2 occurred 3 times, so its probability is 3 over 36, okay. We will repeat the same procedure, okay, with all the values of x bar up to the last value, which is 6. And regarding the 6, if we return back to this table, 6 occurred only once, so its probability is 1 over 36. So by listing all the possible values of x bar, the 11 different values, and by computing their corresponding probabilities, we will construct the probability distribution table of x bar. So now let's try to find the mean of this probability distribution and the variance of this probability distribution. So now we will try to find the mean of x bar and the variance of x bar. Regarding the mean of x bar, we will apply the same rule, summation, but this time this is not x, it's x bar. So this is summation x bar times the probability of x bar. So this is 1 times 1 over 36 plus 1.5 times 2 over 36 plus 2 times 3 over 36 plus 2.5 times 4 over 36 and so on up to the last value, which is 6 times 1 over 36. Okay, adding this will give me 3.5. So the mean of x bar is 3.5. We should notice that this mean, the mean of x bar, the mean of the sampling distribution of x bar, is the same as the mean of x, or the mean of the number of spots that I will get when I roll a die. Once, of course. Okay, so regarding the variance of x bar, the variance of x bar can be found by using the rule of summation x bar minus mu of x bar all square times the probability of x bar. So I will start with the first value of x bar. So this is 1 minus the mean of x bar, this value 3.5, all square times the corresponding probability 1 over 36 plus 1.5, the second value for x bar, minus the mean of x bar 3.5 all square times the corresponding probability 2 over 36 plus 2 minus 3.5 all square times 3 over 6, the corresponding probability, and so on up to the last value in the table. The last value of x bar is 6 minus the mean of x bar, this is 3.5 all square times the corresponding probability, which is 1 over 36. This will give me 1.46. So this is the variance of x bar. Okay, and keep in mind that the variance of x bar, if we compare this variance to the variance of x, or the variance of the number of spots when we roll a die once, we will find that this variance is the same as the previous variance, the variance of x, or sigma square, divided by 2. If I want to get the standard deviation of x bar, I will do this by just taking the square root of the variance. So the standard deviation of x bar is 1.21. Now let's compare the results we got in the previous example. In the previous example, we computed the expected value, or the mean of the number of spots when you roll a die once. This mean was equal to 3.5. When we try to compute the mean of the average number of spots when you roll a die twice, we found that this mean is also 3.5. So this means that the mean of x, the mean of the population you are sampling from, is the same as the mean of x bar. The two values were 3.5. However, regarding the variance of x bar, when we compare the values of the variance of x bar, which is 1.46, the variance of the average number of spots when you roll a die twice, and the variance of the number of spots when you roll a die once, comparing the two values, we can see that the variance of x bar, this value, is the same as the variance of the population you were sampling from, the variance of x, or the variance of the number of spots when you roll a die once, divided by 2. In our example, remember that the 2 was the sample size selected from your population. So we can say that the mean of x bar is the same as the mean of the population you are sampling from. We denoted the mean of the population by mu. And the variance of x bar is the same as the variance of your population divided by the sample size you are selecting from this population. In general, the mean of x bar is always equal to the mean of the population you are sampling from, and we said before that this mean is denoted by mu or mu x. And the variance of x bar is the same as the variance of the original population divided by the sample size. Okay, so this is true in general for any sample size. So we can say that the mean of x bar is the same as the mean of the population. The variance of x bar is the same as the variance of the population you are sampling from divided by the sample size you are selecting from this population. Okay, the standard deviation of x bar can be found by taking the square root of the variance of x bar. Okay, we can call this standard deviation as the standard error of x bar. Now we will talk about the central limit theorem. The central limit theorem will give us more details about the sampling distribution of the sample mean. According to the central limit theorem, the sampling distribution of the mean of a random sample drawn from any population is approximately normal for a large sample size. This means that regardless of the shape of the population you are sampling from, the sample mean will always be normal as long as you are selecting a large sample from this population. By a large sample size we mean a sample of size at least equal to 30. And of course, the larger the sample size is, the more closely the sampling distribution of x bar will look like a normal distribution. So let's clarify the idea of the central limit theorem more in the next slide. Okay, now the figure on this slide. In the first column we have the shape of the distribution we are sampling from. In the first case we are sampling from an exponential distribution. The exponential distribution is one of the continuous distributions. Okay, we did not study this distribution in this course. In the second case we are sampling from a uniform distribution, so the distribution of x, okay, the distribution of the population you are sampling from is uniform. In the third case we are sampling from a U-shaped distribution, okay, and in the last case we are sampling from a normal distribution. We are selecting samples from a population that has a normal distribution. The second, third and fourth columns of this figure show the sampling distribution of x bar when you are sampling from the population samples of size 2. In the third column we are taking samples of size 5, and in the fourth column we are taking samples of size 30. Okay, let's take the first case, when we are sampling from a population that has an exponential distribution. Okay, the exponential distribution takes this shape. In this case, if we are selecting small samples from the population, like samples of size 2 or samples of size 5, it's clear that the shape of the sampling distribution of x bar is not normal. However, if we selected large samples like samples of size 30, then it's clear that the shape of the distribution will look like a normal distribution. This is what the central limit theorem states. Okay, let's take another example. If we are sampling from a U-shaped distribution, then the sampling distribution of x bar, when we select small samples of size 2, it's clear that this distribution does not look like a normal curve. When we are taking samples of size 5, then the shape is not normal. When we are taking samples of size 30, then the shape of the sampling distribution of x bar is like the normal distribution. Okay, so this is actually true in general. Yani regardless of the shape of the population you are sampling from, then the distribution or the sampling distribution of x bar will look like a normal distribution as long as the sample size you are selecting is large. Okay. Okay, what if we are sampling from a normal distribution? What if we are taking samples from a population that looks like a normal, normal? Okay, so if I am originally sampling from a normally distributed population, if this is the distribution of x, okay, then the sampling distribution of x bar will look like a normal distribution regardless of the sample size. So if I'm sampling from a normally distributed population, if the the population distribution of X is normal, then the sampling distribution of X bar is also normal regardless of the sample size. So whether I'm selecting a small sample or a large sample from the normally distributed population, the sampling distribution of X bar will always be normal. So this means if the distribution of X is normal, the distribution of X bar will also be normal for any sample size. And if the distribution of X is not normal, like a uniform, a binomial, or whatever the distribution we are talking about, the distribution of X bar will approximately be normal, but in this case the sample size should be large, and according to the central limit theorem, a sample of size at least equal to 30 will be large enough to apply this approximation. And as we showed in the previous example, the mean of X bar, the expected value of X bar, is equal to the expected value of X, or the expected value of the population we are sampling from, and the variance of X bar is equal to the variance of the population we are sampling from divided by the sample size we are using in this situation. Okay, so as we said before, if X is normal, okay, and you select any sample size from this normal population, then X bar is normal regardless of the sample size, as we said. However, if X is not normal, in other words, if X has any other distribution, okay, than the normal distribution, and you are selecting large samples from this population distribution, then the distribution of X bar is approximately normal, okay. Remember that if X is normal, then to compute any probability related to X, we subtracted its mean, okay, we will subtract its mean and divide by its standard deviation to convert this X to Z, or to the standard normal distribution, and then we can use the standard normal tables to find any probability. We will apply the same formula here. So if X bar is normal, okay, then if I subtracted its mean and divided by its standard deviation, which is equal to sigma over root n, because we said that the variance of X bar is sigma square over n. Okay, so in this case, this formula, if I subtracted the mean of X bar divided by its standard deviation, then this formula will follow the standard normal distribution. And after this transformation, the transformation from X bar to this Z, I can use the standard normal table and I can find any probability related to X bar, like the probability that X bar is greater than 2, the probability that X bar is less than 3, or any other interval, okay? So this formula will help me to compute any probability related to X bar, and as we said before, X bar will follow the normal distribution if the population is normal, if the population we are sampling from is normal, okay? Or if the population is not normal, but in this case I will have to use a sample size of at least 30. So this formula can be applied when the original population we are sampling from is normal, or when the population is not normal, but in this case I will have to take care about the sample size. I will have to use a large sample size, a sample of at least a size equal to 30, okay? And as we can see, this formula depends on sigma. Sigma is the population standard deviation. So this formula is not applicable if the population standard deviation is not known, and we will see in other sections of this course how can we deal with this formula if this sigma, if this population standard deviation is not known. If a worker has observed that the weight of a chocolate is a normally distributed random variable with a mean 32.2, so this is the value of mu, and the standard deviation of 0.3 grams, so this is the value of sigma. If a customer buys one chocolate, what is the probability that it weighs more than 32 grams? So if I want to write this as a probability statement, this will be the probability that X, the weight, is greater than 32 grams, and as we said before, I cannot apply the normal tables directly for this problem. I will need first to convert this X to Z, and then we will subtract the mean and divide by the standard deviation from the right hand side. So let's see the answer in details in the next slide. The answer, this is the probability statement we wrote on the previous slide. We subtracted mu divided by sigma to convert the x to z. From the right hand side we subtracted the value of the mean and we divided by the value of the standard deviation to make the same thing on the right hand side. Okay, so this is the probability that the standard normal random variable, after this subtraction and this division, this right hand side value will be negative 0.67. okay, so on the standard normal curve, as we said, for any normally distributed problem, after this transformation from x to z, I need to graph the area first. So this value is negative 0.67. I will place the negative value on this part of the curve, on the left side of the curve, because it's a negative value. We need the area greater than negative 0.67, so I need to find all the area to the right. Okay, so we said before that the standard normal table is not capable of finding this area. It can find only areas from 0 up to a positive value. So we can write this area to the right as 0.5, the area of this part of the curve, the half of the curve, this 0.5, plus the area from negative 0.67 up to 0. This area is the same as the area from 0 up to 0.67, the positive of this value, because the curve is symmetric. This area from 0 up to 0.67 can be found directly from the standard normal tables. Okay, so we will add a 0.5 to the area we will find from the tables, as we will see in the next slide. This will give me 0.7486. So this value means that we have a 75% chance that a chocolate will weigh more than 32 grams. Okay, so let's now see how did we found this probability from the standard normal tables. Remember, we need the area from 0 up to 0.67. Let's now see how we can find the area from 0 up to 0.67, the area we needed in the previous example. So this is 0.6. This is the second decimal place, 0.07. At the intersection, this number 0.2486 is the area from 0 up to 0.67 on the standard normal curves. Now let's take another example. This example is related to the example we were just solving. Now the customer buys a box of 4 chocolates. Find the probability that the mean weight of the 4 chocolates will be greater than 32 grams. So now we are finding a probability related to x bar, not to x itself, not to the weight. We are computing a probability relating to the mean weight of a sample selected from this population. So the 4 chocolates is considered a sample selected from the population of the chocolates. Okay, and we need to find the probability that the mean weight of the 4 chocolates, so this is x bar, the mean of a sample, is greater than 32 grams. Okay, so let's now solve this problem in the next slide. We have some information. We know that x has a normal distribution, the distribution of the chocolates, the population is normal. This was written or stated in the previous example. Okay, and the mean of the weight of the chocolates is 32.2 grams and the standard deviation of the weights is 0.3. So we know that x has a normal distribution, as we just said. So this means that x bar will be normal, okay, regardless of the sample size, because in this case the sample size is a small sample size, it's 4. But we said that if the sample size is small, x bar will always be normal as long as the original population is also normal. So in this problem, x, the weight of the chocolate, is normal, so x bar, the mean weight of the sample, will always be normal regardless of the sample size. And we said that the mean of x bar is equal to the mean of x, this value, so the mean of x bar is 32.2. We also know that the standard deviation of x bar is equal to the standard deviation of the original x divided by the square root of the sample size. So the standard deviation of x bar is 0.3, the standard deviation of the original population, okay, the standard deviation of the weights of the chocolates, divided by the square root of the sample size, the square root of 4, because the sample size is 4, because we are talking about a box of 4 chocolates. So this standard deviation is 0.15. Okay, what about the probability statement he is asking about? Let's see this in the next slide. Now let's solve the previous example. We need the probability that the mean weight is greater than 32. So this probability is related to x bar, not x, okay, like the previous example. So I will write the probability statement first. This x bar is normal, as we said before, because the original population is normal. To find the probability of any normal random variable, we should subtract its mean, which is the mean of x bar, divide by its standard deviation, the standard deviation of x bar, to convert this x bar to a z. And after this transformation, I can use the tables of the standard normal distribution. So computing this value at the right hand side, we will find that this value is negative 1.33. The second step is to graph this area. On the standard normal curve, the area to the right of negative 1.33 cannot be found directly from the standard normal tables. We need actually to add this part, which is equal to half the area of this part, 0.5, plus the area from negative 1.33 up to 0. Okay, and since the area from negative 1.33 up to 0 is the same as the area from 0 up to 1.33, the area on the positive side, we can go and get the area from 0 up to 1.33 from the standard normal curve, or the standard normal tables, I'm sorry, and then we can add the area we will get from the tables to 0.5. Okay, so let's now go and get the probability that z lies between 0 and 1.33 from the standard normal tables. Okay, so this is the standard normal table. We need the area from 0 up to 1.33, so this is 1.3 from the first column of the table. This is the second decimal place in z. At the intersection, we will find this area, 0.4082, so this is the area from 0 up to 1.33. We can add this value to 0.5 to get the required probability in the question. Now let's take a second example. If the time the students take to come to college has a uniform distribution, where A equal to 70 and B equals to 100, so this is a continuous uniform distribution. The minimum value for the time is 70, the maximum time is 100. Now 40 students are selected from this college. Find the probability that the average time taken by the students in the sample is at least equal to 87 minutes. So the first point, we should look at the probability in the question. Now in this question, he is asking about a probability related to the average time, not the time itself, related to the average time taken by the students in the sample, taken by the 40 students in our sample. We want to find the probability that this average is at least equal to 87. So if I want to write the probability statement following, I need the probability that the sample average x bar, the average time in the sample, is greater than or equal to 87 minutes. Now, if I want to find any probability related to the sample average, up till now we have two rules. The first rule is when the population we are sampling from is normal, and this is not the case in this problem because the time has a uniform distribution. In the second case, According to the central limit theorem, the sample average can also follow a normal distribution if the selected sample size is large, and this is the case in our problem. If we notice the sample size in our problem, sample size is 40, okay? And since the sample size is greater than or equal to 30, then I can apply the central limit theorem and I can say that the sample average is approximately normal, and hence I can apply the normal distribution in this case. So let's move to the answer of this example in the next slide. Okay, so the first step to solve the problem is to find the mean and the standard deviation of the uniform random variable, because the mean and the standard deviation will help us in standardizing the normally distributed random variable x bar. So let's start by the first step. I will compute the mean of the uniform random variable. This is a plus b over 2. This will give me 85. And the standard deviation of the uniform random variable, this is b minus a over square root 12. This will give me 8.66. Now, as we said before, the required probability statement is the probability that x bar, the average time in the sample, is greater than or equal to 87. Okay, this x bar, according to the central limit theorem, will approximately follow the normal distribution because the selected sample size is greater than or equal to 30. Now, to solve the probability of any normal random variable, we said before that our first step is to subtract the mean of this normal variable and divide by its standard deviation. We know that the mean of x bar is the same as the mean of x, the original variable or the population. So the mean of x bar, the mean that I will subtract, is 85. However, the standard deviation of x bar is not the standard deviation of x. I have to divide by square root 40, or the square root of the sample size. So when I standardize this normal random variable x bar, I will subtract the mean 85, but this time I will not divide by sigma. I will divide by sigma over root n, because the random variable we are talking about now is x bar, not x. So I will standardize using mu and sigma over root n. This will move us to this probability statement. The probability that z is greater than 87 minus 85 divided by 8.66 over square root n. So in this step, we converted the x bar to z by subtracting the mean of x bar, which is exactly the same as the mean of x, and dividing by the standard deviation of x bar, which is equal to the standard deviation of x divided by the square root of the sample size. This will give me the probability that z is greater than or equal to 1.46. Okay, so let's try to graph this. So if I try to graph this problem, this is the standard normal curve. This is the value 0, the mean of the standard normal curve. Now the value 1.46 is on the positive side of the curve. This is 1.46. The required area is the area to the right of 1.46, so this is the area I need. Okay, the area to the right of 1.46. So how can I find this area? This is 0.5, the area of half of the curve, as you can see from the graph. This is 0.5 minus the area from 0 up to 1.46. The area from 0 up to 1.46 can be found from the standard normal tables, of course, as we will see in the next slide. By subtracting this area, the area we will get from the tables, from 0.5, we will get the answer of the problem. So let's now see how can we find the area from 0 up to positive 1.46 from the standard normal tables. Now let's try to get the area from 0 up to 1.46 from the table. This is the value 1.4, the first column of the table. This is the second decimal place in Z. At the intersection we will find this value 0.4279. Remember, this is not a required area, this is the area from 0 up to 1.46, so I will subtract this value from 0.5 to get the area greater than 1.46. Now let's move to a new example. In this example, suppose that during any hour in a large department store, the average number of shoppers is 448, the standard deviation is 21. Find the probability that a random sample of 49 different shopping hours will yield a sample mean between 441 and 446 shoppers. Okay, so let's start by defining the variables in this problem and the required probability statement. Now, x in this problem is the number. This is the number of shoppers. Okay, this is our x. The mean of x, the mean number of shoppers, okay, the mean of x is, according to this problem, is 448. The standard deviation of x in this problem, the standard deviation for the number of shoppers is 21. He's asking about a probability related to the sample mean of the number of shoppers. So to write the probability statement, I will write the probability that x bar, the mean of the number of shoppers, lies between 441 as mentioned in the question above and 446. So this is the probability statement. How can I find this probability? First of all, we know that according to the central limit theorem, if the sample size is greater than or equal to 30, the distribution of x bar is approximately normal. So in this problem, let's see the sample size, a random sample of 49 different shopping hours. So this is greater than or equal to 30. So I can assume in this problem that the distribution of x bar is approximately normal. So we know that for any normal random variable, to find any probability related to a normal random variable with a certain mean and a certain standard deviation, I will need to subtract the mean of this random variable, the mean of x bar, and divide by the standard deviation of x bar to convert this x bar to a standard normal random variable. Okay, so let's see the answer of this problem in the next slide. Now the probability we need to find in this problem is the probability that x bar lies between 441 and 446. As we said, x bar is approximately normal, so to convert this normal random variable to a standard normal random variable, I will need to subtract the mean of x bar and divide by the standard deviation of x bar. So let's now try to find the mean of x bar and the standard deviation of x bar. Now we know that the mean of x bar is exactly the same as the original mean, or the mean of the population, or the mean of x, or the mean of the number of shoppers. And the standard deviation of x bar is the same as the standard deviation of x, the standard deviation of the number of shoppers, divided by the square root of the sample size. So in this problem, the mean of x bar is the same as the mean of x, and we know that the mean of x was 448, and the standard deviation of x bar is the same as the standard deviation of x divided by square root n. So the standard deviation of x bar is just 21 over square root 49. So now we can use the mean of x bar and the standard deviation of x bar to standardize x bar. So from the left hand side of the inequality, I will subtract from here, from this value 441, I need to subtract 448, and then I will divide this by the value of 21. I will erase this. Okay, so I will divide by 21 over square root 49. Okay, I will do the same thing on the right hand side of the inequality. So from this 446 I will subtract 448, the mean of x bar, and divide by the standard deviation of x bar, which is 21 over square root 49. So by this we converted x bar to z. So I will compute this quantity. This will give me negative 2.33, and I will compute the value of 446 minus 448 over 21 over square root 49. This will give me negative 0.67. Okay, so we know that the area on the left side of the curve is the same as the area on the right side of the curve, because the curve is symmetric. Okay, so let's graph this. Okay, if this is the graph, okay, and this is 0, the area between negative 0.67 and negative 2.33, so this is negative 2.33. Okay, and this is negative 0.67. Okay, this area in between is the same as the area on the right side, because the curve is symmetric. So now this is the value of 0.67, and this is the value of 2.33. So I can get this area from the standard normal tables. Okay, how can I get this area? I will start by the area from 0 up to 2.33. I will get this area, and from the standard normal tables, as we will see on the next slide, the area from 0 up to 2.33 is 0.4901. So this area, as we will see from the standard normal tables, is 0.4901. And then I will get the area from 0 up to 0.67. This area is 0.2486. Okay, by subtracting this area from 0 up to 0.67 from the area from 0 up to 2.33, I will get the required area. Okay, so let's see on the next slide how can I get the area from 0 up to 2.33, and how can I get the area from 0 up to 0.67 from the standard normal tables. Okay, so now let's know how can we get the area from 0 up to 2.33. This is 2.3, and this is 0.03, the second decimal place in Z. At the intersection, I will find the value of 0.4901. Okay, so this is the area from 0 up to 2.33, and we can get the area from 0 up to 0.67. This is 0.6, and this is 0.7, at the intersection I can mark the area. Okay, so this is the area from 0 up to 0.67. I will subtract the value of 0.2486 from the value of 0.4901 to get the area between the values 0.67 and 2.33, which is exactly the same as the area between the negative values of negative 0.67 and negative 2.33. Thank you.